will now discuss another crypto system that derives its security from the hardness of 0-1 ASIC problem. So what is the problem? Suppose you are given a vector of distinct positive integers. Okay, you can view these as object weights. Now, given a sub-collection AI1, AI2, AIK of these numbers, you can always find their sum, and this S is AI1, AI2, AIK. Okay, so given these weights, you can always find their sum. But the converse problem, the opposite problem, given the sum, determine, if possible, a sub-collection AI1, AI2, AIK having total sum is, total weight is. So AI1 plus AI2 plus AIK, their sum is S. So this problem is hard problem. If the sub-collection is given, finding the sum is easy. But given the sum, the target sum, finding a sub-collection so that their sum is giving S, that problem is hard problem. And this weights, this is not fractional knapsack problem. That means these weights you cannot break. Either you have to take the entire weight, or you have to take AI1 as a whole, or you cannot take this. So it is called 0-1 knapsack. Either you choose this weight or you don't choose. You cannot break it. You cannot take a fraction of this weight. This is 0-1 knapsack problem. So you can reformulate this in subset sum problem. So given the problem instance is you are given the weights A1, A2, AS, AN, and a sum, target sum AS, where A1, A2, AN, and AS all are positive integers. AIs are called sizes or weights, and S is called the target sum. So this is the decision version. Decision version is, the question is you have to answer yes or no. Decision problem means you have to answer yes or no. Means whether there exists a 0-1 vector x, a binary vector x equal to x1, x2, xn, such that x1 a1 plus x2 a2 plus xn an equal to s. So this means this xi's are this x1 is either 1 or 0. If it is 0, then a1 weight is not taken. If this is 1, then a1 weight is contributing to the sum of a's. This is the idea. Okay. So the problem is to find a solution x1 equal x1, x2, xn. This is a binary vector. So that xa, their inner product is s. So given these weights and the target sum, find a binary vector x1, x2, xn such that inner product of xa, ax and a is s. This is a NP complete problem. Okay? This is a very hard problem. Okay? Now, for example, suppose you are given the weights 3, 4, 6, 8, 10, 12. And your sum, target sum is 28. So find the solution. Find the solution. So you can find by trial and error. Trial and error, you can find this 28 means you can take this 12, 10, 6. So the solution corresponding to this is, so this is x1, this is a1 to a6, so this is x1 to x6. So this is not taken, so 0, x1 is 0, x2 is also 0, it is not taken, x3 is 1, x4 not taken, 0, x5 is 1, x6 is 1. Or otherwise the solution, you can take this combination also, 4, 6, 8, 10, that also gives you 28. So this solution, this is your vector. The solution is, feasible solution is either x equal to this or x equal to this. Both of them give you the same target. Okay. So Markley-Hellman knapsack crypto system. Markley-Hellman knapsack crypto system is it consists of the plain text is n-bit strings, n-bit vectors, and ciphertext is non-negative integer. so n length string, n bit string is converted into a ciphertext which is only a positive integer. So as we have already discussed that if Alice wants to send a message confidentially to Bob over public channel using public key encryption, Alice has to use Bob's public key. While encrypting, the encryption should be done using Bob's public key. So what are the public keys here? Bob's public key. Bob chooses super increasing sequence. So A1, A2, An, this is a super increasing sequence of weights. A vector super increasing sequence. What do you mean by super increasing sequence? Super increasing sequence means A1 is less than A1 plus A2. I think I have the definition. Super increasing sequence. Okay. Super increasing sequence. Okay, super increasing sequence is if you take the ith element, it is greater than the previous sum of the previous elements. AI, so A2 is greater than A1, A3 is greater than A1 plus A2, A4 is greater than A1 plus A2 plus A3, like that. AI is greater than A1, A2, AI minus 1. This is example of super increasing. This is the definition of super increasing sequence. A sequence of positive and non-negative integers is said to be super increasing if this relation holds. AI greater than the previous I minus 1 weights, and this holds for all I from 2 to 2, 3 to n. So if you have a super increasing sequence, then the knapsack problem you can easily solve. Okay, so if you have an instance of if your given instance is a super increasing sequence, then you can easily solve the 0-1 knapsack problem. There is an algorithm. The algorithm is shown below. So a knapsack problem with super increasing weights can have at most one solution. It can have at most one solution. Either it has a solution or it does not have a solution. If it has a solution, it will have only one solution. Okay, so how to do that? So if you have, so let me illustrate with example. Okay, so suppose this is super increasing sequence. You can check this. Okay, so this one is greater than 1. This one is greater than sum of the previous 2. This one is greater than sum of the previous 3. Like that, you can check. This is super increasing. Suppose find a solution for target sum to be 27. So what I will do, I will go by greedy approach. So I will first check this one, whether this one can contribute here. So this one is more than this weight I cannot take because my sum value is 27, which is smaller than this. So this value I cannot take. So it is corresponding x6 that bit will be 0. I cannot take this. So I start from the back side. Okay, so I check whether it can be taken or not. In finding this sum, it cannot be taken, it is 0. Then try the next one. Next one, it is less than 27, so I can take this. So corresponding to 1. Now once this 20 is filled, how much is retained? 27 minus 20. That means now my target sum remains 27 minus 20. That means 7. Okay, so my target sum is now 7. So next I check the next one, 9. 9 is more than the target sum. So this weight cannot fit in my knapsack. So corresponding this position is 0. I cannot take this 9. The next one is 4. Yes, I can go for 4 because it is smaller than my target sum. So if I take 4, that means corresponding x3 bit is 1, and then my sum, the target sum is reduced by 4. Already I have taken 4. 7 minus 4, my target sum is now reduced to 3. Okay, then next one is 2. I can fit it in my knapsack because it is smaller than the capacity. This is my capacity, so 3 capacity, so 2 can go, so it is 1. It is 1, so remaining target sum is capacity of my knapsack is 3 minus 1. Already it was 3 and now 2 already filled, so 1. And then this one. So if you have a super increasing sequence, then this solution you can find at most one solution. You can either it will have a solution or it will not have a solution. So the solution corresponding to this, it will have a unique solution. If a solution exists, if the solution is unique. Okay, so the solution here is 1, 1, 1, 0, 1, 0. If you take the sum, the inner product of A and X, you can see the target sum is giving you 27. Okay, so this algorithm is actually written here. This algorithm is written here. If you have a super increasing sequence, then how you find your x values? So from the rightmost bit you start. Okay, from xn you start. So I from n down to 1, you check your capacity. If ith weight can go, if your capacity is more than the ith weight, then ith weight you can take, and corresponding xi will be 1, and you reduce your sum by ai capacity. You reduce your capacity by ai. Otherwise it cannot fit, so xi is 0. So you run this for loop, and if finally if you reach s equal to 0, then this is the solution. Otherwise the solution does not exist. Okay, so this is this already I have illustrated with that example. Okay, so if you have a super increasing sequence, knapsack 0, 1 knapsack problem, you can always you can solve the 0, 1 knapsack decision problem efficiently in polynomial time. So this is also super increasing. If you take the powers 1, 2, 2 square, 2 cube, 2 to the power n, this you can check it is super increasing. And also you can take this exercise. Any super increasing sequence must satisfy ai is greater or equal to 2 to the power I minus 1 for each I. Any ai should be greater or equal to 2 to the power I minus 1. You prove this, try to prove this. And essentially this one is the smallest super increasing sequence. Super increasing sequence. Okay, so let us come back to our Markle-Hellman crypto system. It was designed by Markle and Hellman. Okay, this is my Markle-Hellman knapsack problem. So so public key. So plain text is n-bit string and ciphertext is one non-negative integer. So public key, while encrypting, we have to use Bob's public key. So how the public key and secret key is generated? Let us discuss that. So we choose super increasing sequence. So Bob's public key and secret key I have to set. So what Bob will do? Bob will choose an n length vector, which is essentially super increasing sequence. He first chooses the super increasing sequence, and also choose this integer m, which is greater than sum of all these integers ai, sum of all these sequence elements, summation ai I1 to n. And also it chooses w less than m, is positive integer w less than m, such that w and m are co-prime. Means it is needed to find the for the existence of modular inverse of w, inverse of modular inverse of w modulo m. So these are the private keys of Bob are the super increasing sequence, this m and this w. These are the super increasing sequence. These are the private keys of Bob. Okay, and public key. How public key is generated? So Bob has generated the super increasing sequence, and he is calculating this bi by simply multiplying w with ai. Okay, so from this sequence, A1A2 super increasing sequence, what Bob tries to do, Bob tries to find another sequence of vector, a sequence of elements, non-negative integers, so that it is not super increasing. The super increasing property Bob wants to destroy. So what he does for that, he chooses this W, and so that a W inverse also exists, modulo m, the modular inverse of W modulo m exists. Okay, so this AI is garbled with multiplying with WAI and reduce modulo m. So this is your BI is generated in this way. So this sequence is generated using this AI sequence, super increasing sequence AI. Okay, so this BI is the least non-negative integer satisfying this congruence. Least non-negative, you reduce modulo m, okay, least value. So, so it is clear, public key and secret key. Secret key is a super increasing sequence. This m, which is taken to be greater than summation ai, and W, whose modular inverse, W inverse modulo m must exist. So GCD of WM must be 1. We have to choose W so that the GCD of W and M is 1. And public key simply multiply each AI with W and reduce modulo M. That is your BI. This sequence you generate from AI. So this sequence is the public key, Bob's public key. Okay. Now, while encrypting, Alice wants to encrypt a message. Message is n-bit string. This is a plain text. The plain text is n-bit string. So using the public key of Bob, Alice has to encrypt it. So Alice uses this B1, B2, Bn to encrypt the plain text X, which is X1, X2, Xn n-bit string. So simply take the inner product of X and B. So this is your plain text, which is a bit string of length n, and encryption of X, this plain text, using Bob's public key. Alice is sending the information private message to Bob. So Bob's public key she has to use. Alice has to use. So Bob's public key is this B1, B2, BK. So it's taking this public key is B vector. Okay, so X and B vector inner product is taking. She's calculating the inner product x1 b1 plus x2 b2 plus xn bn. This sum. So Alice is sending this sum. While encrypting, we just take the inner product with the public key, Bob's public key, and send this sum. Now, while decrypting, Bob receives this ciphertext S, and Bob has the secret key. Bob has the secret key, his own secret key, which consists of this super increasing sequence A1, A2, An, and this W and M also. So what Bob does, Bob has to find the plain text, this plain text. So Bob has to solve the knapsack problem. A1, A2. So what he does, he receives this S. He simply multiply this S by W inverse. W inverse S he calculate. If you check this W inverse S, if you say this is S prime, W inverse S equal to S prime, W inverse S is W inverse, S is summation xi bi, summation xi bi. So that means xi, and this is W inverse bi. Now, what is W inverse BI? The way we have calculated this BI, it is essentially W inverse BI is essentially AI modulo M. So, WI inverse BI, this is essentially AI modulo M. So, this S prime, when you Bob receives this ciphertext, and he simply calculate W inverse S. And W inverse S he called S prime. This S prime is essentially the target sum for the subset sum problem, this A1, A2, because it essentially giving you this congruent to summation, this W inverse BI is W inverse BI is AI. So you are getting AI xi modulo M. So you have to solve this subset sum problem. AI xi modulo m. Okay, this is essentially equality. Equality holds because m is greater than summation xi. Means this summation ai. M is greater than summation ai. So even if all the xi's are 1, in that case you are getting the whole sum, summation ai, and m is greater than summation ai. So this modulo m, it has no effect. It's essentially this sum is always less than m. This sum is always less than m. Maximum sum is summation ai. Okay, summation ai. So it is always less than m. So this mod effect is not there. So it is essentially we are getting equality. Okay. So given this target sum and the super increasing sequence A1, A2, AN, you have to solve this knapsack problem, whether there is a solution. Okay, that solution will give you the plain text. Okay, so mind that decryptor, that means Bob has his own secret key, that means the super increasing sequence he has, and this target sum he calculates, which is essentially target sum for this sequence, and since it is a super increasing sequence, Bob will be able to get the solution, unique solution he can always get, and that solution is the plain text. Okay, using that algorithm, finding 0, 1 knapsack problem, you apply that 0, 1 knapsack problem for the super including sequence. You can get this plain text. Okay. So the main, so this is, there are many other variants also. I have just explained only one variant. Sometimes this here during encryption I have done the during encryption I have taken only one integer and take the modulo m operation here. So in some cases it is done in a different way. Okay? The basic idea is same. Okay. Now here what I have, 0, 1 knapsack problem. So plain text. Okay, so one exercise is done here. One exercise is given here. Suppose your super increasing sequence, your private key is given. Private key is given. Private key, that means super increasing sequence 3, 5, 9, 18, 36, 100. You can check this is super increasing. 5 is greater than 3, 9 is greater than the sum of previous 2, 18 is greater than sum of previous 3, like that. Okay. And m also, suppose m you have taken 201 and w you said 71, and this 71 must be co-prime to 201. Now while decrypting, you need to find the inverse. W inverse you have to know. Okay, for decrypting, W inverse you have to know. Now what will be Bob's public key? Bob's public key will be simply all these elements multiply by W and take modulo 201. So this sequence, from this sequence you can get the sequence B. Now if this is your plain text, what will be the cipher text? Okay, so if this is your plain text, your cipher text will be simply the inner product of B, whatever you get, with this. Okay, so Bob's public you find, then take the inner product with this, you get the cipher text. And decryption process, also verify decryption process. Okay, when Bob receives the cipher text of part B. So when whatever cipher text you get, this is one positive integer. Okay, so that positive integer you have to multiply with 77 inverse. Okay, so 77 inverse times the cipher text you receive, So you generate the cipher text here, and you find W inverse, that means 77 inverse modulo 201 using extended Euclidean algorithm. and that 77 inverse whatever you get, you multiply it with the ciphertext you obtain here. Okay, so whatever, so you get an integer. That integer essentially is the target sum for this super increasing sequence. Okay, so you solve the knapsack, the 0 1 knapsack problem given this sequence and the target sum that you calculate by multiplying the ciphertext with W inverse. Okay, so decryption process also you can verify that actually you are getting back this ciphertext, this plain text or not. Okay, you do this exercise. I will give you some assignments, quiz in the form of quiz. You can solve those also. What I have done here, 0 1 1. This is something your target sum, suppose 63. Super increasing sequence is this. Now, how to solve the super increasing sequence? It is illustrated with another example. Already we know how to do that. Okay, already we have explained how to do that. So this type of problem I may ask in exam, okay, in class test actually. Okay, one example is illustrated. The Markle-Hellman knapsack problem is illustrated with this example. Okay, so I have this super increasing sequence. M is specified, W is also specified, and this W is co-prime to this. Okay, this is defined, and this M should be chosen greater than summation of this. Otherwise, during decryption, you will have problem. You will not get exact equality. Okay. Target sum, you need the target sum. You need during decryption. Actually, what we are doing for this sequence, we construct the target sum by multiplying W inverse with the received ciphertext. Okay, so that target sum exact equality we need. Okay, so just once again go through this. So when we multiply the received cipher, this is your received ciphertext. So from this received ciphertext, we construct a target sum S prime for this super increasing sequence. Okay, so S prime is W inverse S. So when you calculate all these values, here we get congruent modulo M, because BIs are generated using taking modulo M operation. Now this AIs are chosen to be greater, M is greater or equal to summation AI. So this modular M does not have any effect. Okay, even if all the x's are 1, in the worst case all the x's are 1, it is actually equality holds. So you get a target sum, exact target sum, this one. To solve this, you get this unique solution. Because unique solution, why? There will be no ambiguity, because given a super increasing sequence and target sum, the 0 1 knapsack has either no solution or it will have unique solution. If it is not properly computed, then it is you will not get back this, and if you get back this, only one solution exists. So while decrypting, you will get only one. You can recover the plain text. Either you will be able to recover it uniquely, or you will not be able to recover it. Okay. So it is illustrated here. Bob's public key you can calculate. Bob's public key is simply all these values multiplied by 38 modulo 101. So this is 38 into 2, 38 into 4. If it is more than 101, you reduce it. Okay, take modulo. So this BIs you generate 38, 76. Then this is, so this sequence generate. Okay, this is simply W times this A1, A2, A6, this sequence, the modulo 101. This sequence you get. Now next question was, if Alice and Bob, Alice uses Bob's public key to encrypt the plain text disk. This is your plain text. Determine the resulting ciphertext. This is very easy. Whatever Bob's public key you have, you just take the inner product with this. Okay, so Bob's public key is this. Bob's public key is this, and you are taking one. This is one position. This is, so this 3 you are taking, and the last one you are taking. So this is your ciphertext. This is one positive integer. Okay, and the next problem is perform the decryption process that would need to be done when Bob receives the ciphertext of part B. So for decryption, you need W inverse. You need W inverse. W inverse modulo 101. You have to calculate. Okay, so for that you cannot do it by hand. Okay, so you have to use extended Euclidean algorithm here. Using extended Euclidean algorithm, you can quickly find the modular inverse. So that inverse, when you multiply with the received cipher text, 172 times this 8, multiply modulo 101, you can you get 63. Okay. You get 63. So this is essentially you have to solve the solve this given instance 1, 2, 4 this with this target sum. Okay, so this I think this is done here. Here I have done that part is done here. That part is done. So the target sum is 63. Super increasing sequence is this. You apply the algorithm for 0, 1 knapsack. Okay, so now knapsack size is 63, capacity is 63, so 48 you can take. This is 1, corresponding x is 1, x6 is 1. Then your sum is reduced by 48. So 63 minus 48, your capacity is now 15. So it cannot fit 20, next one 20 cannot fit. Previous one it cannot fit, so corresponding xi is 0. Then the previous one 9 it can fit. Okay, it can fit, so 1 and reduce by 9, capacity reduced by 9. Then 4, yes it can fit and reduce capacity reduced by 4, 6 minus 4 2. Then you take the whole capacity is now filled, s is s prime is 0, so it is 0. So this is your solution and this is the plain text. Okay. Okay, so I think I have done, I have completed this. I have completed this. I will send you some assignments, okay, on RSA, El Gamal, knapsack problem, means the Markley-Hellman knapsack crypto system, and also we have covered several algorithms that we essentially need while doing this encryption, calculating the ciphertext or recovering the plain text. So those algorithms, some problems related to those algorithms, I will set some questions and I will send you as a quiz. Okay. Another crypto system we will discuss in the next class, that is Rabin's crypto system, and that is actually that is based on factorization hard, the difficulty of factorization of large integers, but additionally it also uses quadratic residues. Okay, so some number theory related to quadratic residues we have to go through. And the Chinese remainder theorem is also used in finding the square roots. Okay, so square roots, quadratic residues, we have to go through some number theory related to those. Okay, so in the next class, we are going to start